Hello dear students, welcome to mathematics class. In this class, let us discuss some properties of Riemann integrable functions. In that, the first one is, if f of x and g of x are bounded and integrable in the closed interval a b, then f of x plus g of x is bounded and integrable in the same interval a b, and also show that integration over a to b f of x plus g of x dx is equal to integration over a to b f of x dx plus integration over a to b g of x dx. So, here in this theorem it is given that the two functions f of x and g of x are bounded and integrable, then their sum, that is f of x plus g of x, is also bounded and integrable, and integration of the sum of two functions is equal to sum of two integrals, that is integration over a to b f of x plus g of x equal to integration over a to b f of x plus integration over a to b g of x. So, it is the given theorem. So, now let us prove this one. Since f and g, which are the given functions, are bounded on the closed interval a b. So, here it is given that the two functions f and g are bounded. Then by using the properties of bounded functions, we can say that f plus g is bounded on the closed interval a b. So, now here since f and g are bounded, then by using the algebra of the bounded functions, we can say that f plus g is bounded function. Now, let p is equal to a equal to x naught, x1, x2 and so on xn equal to b be a partition of closed interval a b. Now, let us consider the partition P consisting of the points x0, x1, x2 so on up to xn, where xn equal to b and x0 equal to a. Now, let small mr dash capital Mr dash be the infimum and supremum of Mr dash and capital Mr dash be the infimum and supremum of the function f on the rth subinterval, that is IR. Now, let us consider the infimum and supremum of the function f on the rth subinterval as small mr dash capital Mr dash and small mr double dash capital Mr double dash be the infimum and supremum of the function g on the rth subinterval. Here Mr double dash and capital Mr double dash. So, they are the infimum and supremum of the function g on the rth subinterval, and small mr capital Mr be the infimum and supremum of f plus g on IR. So, here we have three functions. The first one is f, g and f plus g. So, corresponding to f, g and f plus g, we have considered different infimum and supremum. First Mr dash and capital Mr dash. So, these are the supremum and infimum of the function capital F. Mr double dash and capital Mr double dash, these are for the function g, then Mr and capital Mr. So, these two are the infimum and supremum of the function f plus g. Now, Mr dash, Mr double dash are supremum of f, g on I r. So, here these two are the supremums of the function f and g on the rth subinterval. Now, it implies that f of x less than or equal to mr dash and g of x is less than or equal to mr double dash. It is for all x belongs to the rth subinterval. So, this is by the definition of supremum, because supremum is, that is the upper bound of the function. Now, here it is mr dash and capital mr dash, they are the supremum of the function f and g on the rth subinterval, then they must be greater than or equal to the given function, means all the values of the function f of x must be less than or equal to mr dash and all the values of g of x must be less than or equal to mr double dash. So, this condition must be true for all values of x in the rth subinterval. Now, it implies that f of x plus g of x is less than or equal to mr dash plus mr double dash. By adding the above two inequalities, we get f of x plus g of x less than or equal to mr dash plus mr double dash. So, it is also for all values of x in rth subinterval. Now, we can write this function as f plus g of x less than or equal to mr dash plus mr double dash. So, therefore, now here we got f plus g of x is less than or equal to mr dash plus mr double dash, means here it implies that this mr dash plus mr double dash is the upper bound of the function f plus g, because the values of this f plus g of x is always less than or equal to this value, means this becomes the upper bound for the function f plus g. And now, let us continue. Here, given that, or we have considered that capital mr is supremum of f plus g on I r. Now, it is our consideration, that is capital mr is the supremum of f plus g on I r. So, here supremum means it is the LUB, means least upper bound. So, now in the previous equation we got that f plus g of x is less than or equal to mr dash plus mr double dash, means this value is the upper bound of the function f plus g and this mr is the least upper bound of the same function. Then we can write that it implies that mr is less than or equal to mr dash plus mr double dash. So, since this mr dash plus mr double dash is simply an upper bound of the function f plus g, but here this mr is the supremum or least upper bound. So, therefore, least upper bound is always less than or equal to all the upper bounds. So, therefore, mr is less than or equal to mr dash plus mr double dash. So, this is on the rth subinterval. Now, let us find the upper Riemann sum for the function f plus g. So, here we know that u p f plus g. So, here this is the upper Riemann sum for the function f plus g in the interval, sorry, in the partition p. So, therefore, by the definition of upper Riemann sum, we can write this one as summation over r is equal to 1 to n mr into delta r, where mr is the supremum for the function f plus g and delta r is the length of subintervals of the partition p. Now, this can be written as less than or equal to summation over r is equal to 1 to n, this is mr dash plus mr double dash into delta r. So, here we have replaced this mr. This mr is less than or equal to mr dash plus mr double dash. So, therefore, this equation or this summation becomes less than or equal to summation over r equal to 1 to n mr dash plus mr double dash. Now, this is equal to summation over r is equal to 1 to n mr dash delta r plus summation over r is equal to 1 to n mr double dash into delta r. Now, again by using the definition of upper Riemann sum, this mr dash is the supremum of the function f and mr double dash is the supremum of the function g. So, therefore, this summation is nothing but this is the Riemann upper sum for the function f and this is the Riemann upper sum for the function g. So, therefore, this can be written as UPF plus UPG. This is the upper Riemann sum for the function f, upper Riemann sum for the function g, because here we have the supremum of the function f and here it is the supremum of the function g. So, therefore, it implies that UPF plus g less than or equal to UPF plus UPG, because this is the upper Riemann sum of f plus g and this is less than or equal to this value means. So, therefore, that is nothing but UPF plus g is less than or equal to UPF plus UPG. Similarly, we can prove that LPF plus g is greater than or equal to LPF plus LPG. So, it is the inequality for lower Riemann sum of the function f plus g. So, therefore, lower Riemann sum of the function f plus g is always greater than or equal to lower Riemann sum of the function f and lower Riemann sum of the function g. Now, let us consider the oscillatory sum of the function f plus g. So, that is W of p f plus g. This is the oscillatory sum and this can be written as the difference of upper Riemann sum and lower Riemann sum. So, therefore, WP f plus g is equal to UP f plus g minus LP f plus g. So, here this is the oscillatory sum of the function f plus g. And now by using these two inequalities we can replace this statement or this expression as less than or equal to, this is nothing but UPF plus UPG minus, and here this is nothing but LPF plus LPG, because this is less than or equal to. So, therefore, this is less than or equal to UPF plus UPG and here we can substitute this value as LPF plus LPG and this is less than or equal to. Now, here we can rearrange the terms. Here we can write this one as UPF, here it is minus LPF. We are collecting the upper Riemann sum and lower Riemann sum of the same function on one side. This is the upper Riemann sum of the function f and this is the lower Riemann sum of the function f. Then plus here it is UPG, this is the upper Riemann sum of the function f and here plus into minus becomes minus LPG. So, therefore, it is UPF minus LPF plus UPG minus LPG and this is less than or equal to UPF minus LPF is nothing but that is the oscillatory sum of the function f, that is given by WPF plus WPG, because UPG minus LPG, that is nothing but oscillatory sum of the function g and here it is the oscillatory sum of the function f. So, therefore, oscillatory sum of the function f plus g is always less than or equal to oscillatory sum of the function f plus oscillatory sum of the function g, and consider this as equation number 1. And now So, here we have proved that the oscillatory sum of the function f plus g is less than or equal to oscillatory sum of the function f plus oscillatory function of the sum of the oscillatory sum of the function g, and consider this as the equation 1. And now let us continue. Since f and g are integrable on the closed interval a b. So, here it is given f and g are the integrable functions. Therefore, there exist partitions p1 and p2 of the closed interval a b such that w p1 f less than epsilon by 2 and w p2 f is less than epsilon by 2. So, here w p1 f means that is nothing but L p f minus u p f, and here w p2 f, that is u p2 f minus L p2 f. Now, since f and g are integrable functions, then there exist the two partitions p1 and p2 of the interval a b, satisfying the condition that w p1 f, w p1 f means that is u p1 f minus L p1 f is less than epsilon by 2, and here it is u p2 f minus L p2 f is less than epsilon by 2, and this we are writing by using the condition that necessary and sufficient condition for integrability, that is UPF minus LPF is less than epsilon. So, here it is the necessary and sufficient condition for the integrability. If f is integrable, then this condition must be true, or if this condition is given, then f is integrable. So, here f is already integrable means this must be holds good for the function f. So, therefore, here w p1 f, so it is the condition for integrability of the function f, and here this must be, that is w p f. So, therefore, these two are the conditions for the integrability of the two functions, that is w p1 f and w p2 f. They are the two partitions of the closed interval a b. Now, let p dash, where p dash is the union of p1 and p2, then w p dash f is less than or equal to w p1 f, which is less than epsilon by 2. So, here p1 union p2, that is nothing but the p dash, where p dash is the refinement of p1 and p2, because that p dash is the greater partition than p1 and p2. So, therefore, here p1 is greater than p dash is greater than p1 and p dash is greater than p2. So, therefore, we can write oscillatory sum of the function function f in the partition p dash is less than or equal to oscillatory sum of the function f in the partition p1, since p dash is the refinement of p1. And similarly, we can write that w p dash g for the function g is less than or equal to w p2 g less than or equal to epsilon by 2. So, here make one correction that for the partition p2, consider this as the function g, that is w p2 g less than epsilon by 2, and here u p2 g minus L p2 g less than epsilon by 2. So, therefore, here w p dash g less than or equal to w p2 g less than or equal to epsilon by 2. Now, consider this as equation number 2 and this as equation number 3. Now, using equation 1, we have w p dash f plus g is less than or equal to W P dash F plus W P dash G. So here in the equation 1, that is nothing but W P F plus G is less than or equal to W P F plus W P G. It is our equation 1. Now here we are writing this equation for the partition P dash. So therefore W P dash F plus G less than or equal to W P dash F plus W P dash G. Now here these two are less than epsilon by 2 plus epsilon by 2 by using the equations 2 and 3. So therefore this one is less than epsilon. Now this is nothing but W P dash F plus G is less than epsilon, and we can write this as upper Riemann sum of the partition F plus G minus lower Riemann sum of the function F plus G is less than epsilon, and by necessary and sufficient condition it implies F plus G is integrable. So here W P dash F plus G, it is the oscillatory sum of the function F plus G. Oscillatory sum means that is the difference of upper Riemann sum minus lower Riemann sum, which is less than epsilon. So therefore by using the necessary and sufficient condition we can say that F plus G is integrable. And now we need to prove that already now we have proved F plus G is bounded and F plus G is integrable. Next we need to prove that integration over a to b f of x plus g of x is equal to integration over a to b f of x plus integration over a to b g of x. Now let us continue. Now let epsilon greater than 0 be given, then there exist partitions P1 and P2 of the closed interval AB such that, so here let us consider the epsilon which is greater than 0, then there exist two partitions P1 and P2 of the closed interval AB such that integration over a to b f of x dx minus epsilon by 2 which is equal to integration over bar a to b f of x dx minus epsilon by 2 is less than L P1 f. So here this is by using the Darboux theorem. So here it is the statement of the theorem. Now if f is bounded function, then for each epsilon greater than 0 there exists delta greater than 0. Delta is nothing but length of each sub interval in the partition P such that LPF is greater than integration of bar a to b f of x dx minus epsilon. Since epsilon is arbitrary, we can take epsilon by 2 or epsilon by 4 any value as per our convenience. So here we have considered epsilon by 2. Now here integration over a to b f of x dx minus epsilon by 2 we have considered, and in place of integration over a to b here we have considered bar a to b f of x dx. This is because the function f is Riemann integrable, and if the function is Riemann integrable then its lower Riemann integral is equal to upper Riemann integral. So therefore, and those two values are equal to the common value of the integral. So here it is the common value of the integral, then we can replace this integral by bar a to b f of x dx minus epsilon by 2, and this one is less than L P1 f, that is the lower Riemann sum of the function f in the partition P1. Then integration over a to b g of x dx minus epsilon by 2 is equal to integration over bar a to b g of x dx minus epsilon by 2 less than L P2 f. So, this is also by using the same Darboux theorem, and here we have replaced the function f of x by g of x. Now, if P is equal to P1 union P2, then L_P1f less than or equal to L_P_f and L_P2g less than or equal to L_P_g. So, now P is the union of these two partitions, means this P is the refinement of these two partitions, because that is the greater partition. So, therefore, L_P_f, here it is L_P1f less than or equal to L_P_f and L_P2g is less than or equal to L_P_g, that is the partition P. So, therefore, integration over a to b f of x dx plus integration over a to b g of x dx minus epsilon by adding these two integrals or these two equations is less than, here this is less than L_P1f, that is L_P1f plus L_P2g. So, therefore, now adding these two integrals, we got integration over a to b f of x plus dx, integration over a to b of g of x dx minus epsilon by 2 minus epsilon by 2, that becomes minus epsilon, which is less than L_P1f plus L_P2g. So, here this is not f, here this is the function g, that is L_P1f plus L_P2g. Now, this is less than L_P_f plus L_P_g, because L_P1f is less than L_P_f and L_P2g is less than L_P_g. So, therefore, here we can replace these two lower sums by L_P_f and L_P_g. So, therefore, this total quantity is less than or equal to L_P_f plus L_P_g, and this can be written as this L_P_f plus L_P_g is less than or equal to L_P_f plus g, and this is less than or equal to integration over bar a to b f plus g of x dx. So, here this can be, we have already proved that UPF plus G is less than or equal to UPF plus UPG, and similarly LPF plus G is greater than or equal to LPF plus LPG. So, therefore, this one is less than or equal to LPF plus G. Now, here LPF plus G means it is the lower Riemann sum of the function f plus g, and integration over bar a to b f plus g of x by using the definition of the lower Riemann integral, we can say that this is the supremum of all the lower sums. So, here by the definition bar a to b f of x dx is nothing but supremum of LPF, is it right? This is the definition of the lower Riemann integral. Supremum means that is the greater value, because that is the greatest lower bound. So, therefore, all the lower sums must be less than or equal to this lower Riemann integral, that is bar a to b f plus g of x, and this is equal to integration of a to b f plus g of x dx, because already we have proved that f plus g is integrable. We have proved that f plus g is integrable. Since f plus g is integrable, then lower Riemann sum of that function is equal to upper Riemann sum of the same function, and those two lower and upper Riemann integrals are equal to the common value of the integral, that is integration over a to b f plus g of x. So, therefore, it implies that integration over a to b f of x dx plus integration over a to b g of x dx is less than or equal to integration over a to b f plus g of x dx. So, here in this expression we are excluding epsilon because epsilon greater than 0 is arbitrary. Arbitrary means it can take any value. So, therefore, consider epsilon is equal to 0. So, therefore, here if epsilon is 0, then on LHS only these two integrals will remain, that is integration of a to b f of x dx plus integration of a to b g of x dx, and that is less than or equal to integration of a to b f plus g of x dx. Now, we need to prove that these two are equal. Now, we have proved that this one is less than or equal to f plus g, and in the next part we need to prove that f plus g is less than or equal to f of x plus g of x. Now, and here we have consider this as equation number 4. Replacing f by minus f and g by minus g in equation 4. Now, replace f by minus f and g by minus g in the equation 4. So, therefore, that becomes integration over a to b minus f of x dx plus integration over a to b minus g of x dx is less than or equal to integration over a to b minus of f plus g of x dx. Now, multiply this inequality by negative sign. So, then that becomes minus of minus, that becomes plus, here also same, but this less than or equal to becomes greater than or equal to, because we are multiplying with the negative sign. Multiplying negative sign to the above inequality. So, therefore, it becomes integration over a to b f of x dx plus integration over a to b g of x dx is greater than or equal to integration over a to b f plus g of x dx, and consider this as equation number 5. Now, from equations 4 and 5, in equation 4 we have this LHS is less than or equal to RHS, and in equation 5 LHS is greater than or equal to LHS. On combining those two results, we can write that integration over a to b f of x dx plus integration over a to b g of x dx is equal to integration over a to b f plus g of x dx, or we can write this as integration over a to b f plus g of x dx is equal to integration over a to b f of x dx plus integration over a to b g of x dx. So, therefore, it is the theorem. In this theorem, it is given that f and g are bounded and integrable. Then we need to prove that f plus g is also bounded and integrable, and after that we need to show that this integral, that is integration over a to b f plus g of x dx is equal to integration over a to b f of x dx plus integration over a to b g of x dx. So, now this is the theorem required.